going to look at a very specific type of problem that looks at the heating and cooling of buildings. The idea is we want a model that describes the 24-hour temperature profile inside of a building. So in order to do this, there's a couple of things that we need to consider. The first thing we need to consider is what is the outside temperature. Another thing we need to consider is the heat that's generated inside of the building, whether that be from the machines inside the building or the people inside the building, things like that. And then the third one, furnace heating or air conditioned cooling, to actually heat or cool the building. So in order to actually do this, we're going to want to answer 3 questions. Our first question, how long does it take to change the building temperature substantially? This is going to depend on a lot of different things, but how long does it actually take to make a substantial change in the building temperature? Our next question, how does the building temperature vary during spring and fall when we assume we don't have any heating or air conditioning going on? And then how does the building temperature vary during the winter when we assume there's a furnace heating and summer when we assume there's air conditioning going on? So these are the 3 things we want to look at. So let's start to look at the idea of how to do this. So we do want to use compartmental analysis like we discussed before. And capital T of T we're going to use to represent the temperature of the building at time t. And our rate of change is going to be determined by all the factors that either generate or dissipate heat. So let's slowly look at all of these different factors. The first factor we're going to consider is the heat produced by people, lights, and machines inside the building. And these things cause an increase in temperature. People, lights, and machines inside the building are going to increase the temperature in the building. And we're going to denote this factor by H of T. The next factor we'll consider is the heating or cooling supplied by either the furnace or the AC. And we're going to denote this factor by U of T. Our heating rate and our furnace rate, so H of T and U of T, are often given to us in terms of energy per unit time, such as something like thermal units per hour. We can multiply these by our heat capacity of the building to get these things in terms of temperature per unit time. The third factor we need to consider are the effects of outside temperature, and this is denoted by M of T. And experimental evidence has shown that this part can be modeled using Newton's law of cooling. And this law says that the rate of change in the building temperature M of T is proportional to the difference between the outside temperature M of T and the inside temperature T of T. So we have K times M minus T. And this K is going to depend on a lot of physical properties of the building, like the number of doors, the windows, the type of insulation, things like that. But it doesn't depend on M, capital T, or little t. So when the outside temperature is greater, then we have that this number is positive. It's going to increase the building temperature. On the other hand, if the outside temperature is smaller, this term is going to be negative, and the building temperature will decrease. So now let's summarize everything we've looked at. So far we have that the rate that the temperature is changing inside the building with respect to time is equal to K times M of T minus T of T, that term that has to do with the outside temperature, plus H of T, which has to do with how the people and lights and machines are generating temperature. And then plus U of T, where U of T is determined by the furnace or the air conditioner. This H of T term is always going to be greater than or equal to 0. These things should always be generating heat. There's never going to be anything inside the building that's causing the building to lose heat. We also have that U of T is positive for furnace heating. If we're heating the building, the U of T will be positive, and it'll be negative if we're running an air conditioner to cool the building. So let's look at actually solving this. We can rewrite this differential equation to be in standard form. That gives us that the derivative of capital T with respect to little t is equal to P of T times capital T of T is equal to Q of T. where P of t is equal to k and Q of t is equal to k m of t plus h of t plus u of t. Our integrating factor is mu of t is equal to e times the integral of P of t dt, or the integral of k dt. The integral of k dt is just kt, so I have that my integrating factor is e to the kt. Multiplying through by this integrating factor gives me e to the kt times d capital T over d little t, plus k e to the kt is equal to e to the kt times q of t. Using the properties of solving linear differential equations, we can integrate both sides. That gives us e to the kt times capital T of t is equal to the integral of e to the kt times q of t dt plus c. Solving for capital T of t, I then get e to the negative kt times the integral of e to the kt qt dt plus c times e to the negative kt. Or we can rewrite that as capital T is equal to e to the negative kt times the integral of e to the kt times kmt plus ht plus ut dt plus c.